a Tesla, I never gave a fuck. I keep a
Okay
chopper
guys,
right
we're gonna
next to
talk
slam
about
like a
clearing a
wrestler, nigga, I'll
binary
rip you
search
up.
tree.
You know I'm a big
We can
dog,
then search for a
nigga, you
key
ain't
stored
number
in
pup.
a binary
Yeah, you
tree.
run up on me, I leave you in the pool of your blood.
Besides the search operation, which
I put
binary
that
trees
pistol in
can
your
support,
mouth and then pull
such
my
as
dick in your
minimum,
sister.
maximum,
I'm
successor,
a
and
sick
predecessor,
motherfucker, young.
in this section we shall examine these operations and how to support each one in O of each time for any binary tree of height h. So searching. We use the following procedure to search for a node. Give it a pointer at the root of the key k. Tree search returns a pointer to the node k key k if one exists, otherwise no. What it does is it queries the binary search tree, searches for the key. Let's assume in this case it's going to be 13. Since 13 is less than our root, we will go to the left. Then, since 13 is greater than 6, we'll go right. Since it's greater than this node, we'll go right. And we'll check, since it's equal, this is the node that we have found. This is the way that we search. Implementing this into code, we would run a while loop, and while node.max equals, and instead of this, I think the way that they implemented it, they called it as a recursive function, so we could do that as well. Simply just calling each node their child to make it easier. So if x, the way that is x equals null or k equals x dot k, then we return simply just x, which is null or the key itself. If k is less than x dot key, then we go to the left of the tree house. We assume it's larger or equal, thus we go to the right of the tree. And we can completely iterate this process until we find or we get null. The procedure begins the search at the root and traces a simple path downwards. And because of this, each time it goes down a layer, each time the for loop or recursive function is called, it goes down a layer. That's why it is O of h time, h corresponding with height. Again, we could write this procedure using the while loop like I was talking about earlier. And the iterative version is more efficient, however, on other computers. So that's why while is usually better. So the iterative is while x is not equal null and k is not equal key, we just go k is less than key, x is equal to x to the left, x equals to right. Simply, we just iterate through the tree until we find it. If we find it, great. If not, and it's null, then we just go and we return null. I personally think that this is a better opinion, simply because it allows you to go through the for loop or go through the loop over and over again without having to recall a function, which can definitely take some header or load in the program. So find maximum and maximum of a binary search tree. Usually we can look at two places. We'll have to look at the leaf nodes, or we can simply just look at the root. So we can always find an element. Tree's minimum by following the left pointers from the root until we encounter a nil. Oh, my apologies. If you go left, always you get root lowest, then right, you get the highest value. So why left doesn't go null, you just literally just go completely left and then you get it. Likewise for the maximum, you see we're using the while statement over here, rather than, we could also write this as an iterative statement like we did earlier, but honestly it's better if we do it this way. Both of these procedures run OH time, again, because every time we call the function, we go down a layer. So successor and predecessor, this is probably the most important one. Given a node in a binary tree, sometimes we need to find the successor and also in the sorted order determined by an in-order tree walk. All keys are distinct. The successor of a node x is the node with the smallest key greater than x dot key. Successor to node x. All keys are distinct. The successor of a node x is the node with the smallest key greater than x dot key, which makes sense. So the binary tree allows us to follow the successor without even comparing keys, because we always know it's always down. So the following procedure returns the successor node x if it exists. X has the largest key. So if right does not equal in this, then you go nil, and x dot p. For while is not null, and x got right, then you will simply go down the path to the right. If I knew what x dot p meant, that would be better. I'm gonna check over this code a little later. We break the code for tree successor into two cases. If the right subtree of x is non-empty, then the successor of x is just the leftmost node. If that makes sense, the right tree is non-empty and it has stuff both sides. Assume we're finding the successor of the root. It's the leftmost node and the right subtree. Go right, then we have to go left. This is important. Successor goes to left most in right, simply because this is shown to be the smallest value that is highest in this tree, and which is why we delete in a certain order. When we delete a node, the one that usually replaces the root or a certain node that we delete is the leftmost right of that node. For example, successor of a node with key 15 is, where did the key 15 go? Okay, successor of this would be that 9 over here. Or I guess since this goes left, it would be this 13. Right? Because that looked like it went right. My fault. But it's going to be that 13. I'll go back at 2 minutes after I finish this. Is that fun? Okay. So on the other hand, of the right, if x you show if the right subtree is empty, then and x has a successor y, then the lowest ancestor of x, whose left child is also an ancestor of x. So yeah, in figure 12.2, the successor of the node with key 13 is the node with key 15. Find y, we simply go up a tree from x until we encounter none left child of its parents. The running key of this is scan O of h since we go up and down, which is and the procedure for true predecessor is symmetric to successor, we do the opposite. Even if the keys are not distinct, we define successor and predecessor as node x as returned by calls made to tree successor and tree predecessor respectively. Thus, this is a following algorithm. We'll go a little bit later.